Oops. Next to share, and then move over here.
Yes.
Is that okay?
Yes, now look through, yeah.
Okay, first of all, hi everybody, and let me thank you, the organizer, for setting up this wonderful meeting. It's been a wonderful opportunity, and for me, they don't know, but it's also a birthday present. Okay, and the following, I'm going to show you the latest results we are obtaining. This is the group is working on this target, M192, which consists in what we are getting out of new Iran NOEMA observations. Let's first review what is this target. For me, is one of the best example of what PPN is. In the optical, you see this bipolar reflecting nebula. And in fact, here you see the only big asymmetry in the object, because the southeast lobe is a little bit fainter than the northwest, just because in the middle there is a thick equatorial structure. I wouldn't say torus or this. You will see later what do I mean with the structure that is partially obscure in the south lobe. In addition to the reflected light in the walls of these cavities, you can also detect emitting lines of O1, S2, and 2, O3, even molecular hydrogen, I mean vibrational excited molecular hydrogen, iron, and even phi-free at low frequencies. Two sort of clamps, one in the north, one in the south, not exactly looking the same, but sharing more or less the same properties, and where an expansion velocity of 170 kilometers per second has been detected. Probably these are due to chokes in the jet that is presently active. The present mass loss is very low, is several times 10 to the minus 13, and is shown as a fast wind that you can detect in H alpha at the base of the lobe. For the time being, the central star remains single. There is no evidence for being a binary, although of course we love to see a binary here. And the distance has been computed based on the standard luminosity, but is consistent with the result from Gaia. If on the contrary, you look at the molecules, then the object is totally different. If you reconstruct where the molecular gas is placed, then this is shown in this plot with the black contours. You see that the molecular gas is just surrounding the reflecting lobes, and you see a emission blob in both tips, and then a thick equatorial structure in the middle. The total mass in this gas is nearly 1 solar mass, and in fact, just in the lobes, which are expanding faster, we already have 0.7 solar masses. So this is a huge, very massive object. Another characteristic of the object is that it presents a linear velocity gradient that is also characteristic of many of these sources. And if you do the depth projections, the expansion velocity for both tips are around 70 kilometers per second. The energy and the momentum in this gas is huge, and in fact, it was the first source in which we realized that it was impossible to explain that just invoking radiation pressure. Radiation pressure on the grains is the mechanism at work in the AGB phase, so something has happened at the PPN phase, so the acceleration could take place. In fact, if you assume that this constant velocity is due to a sudden event, then the kinematical age is 1200 years, and that will be the responsible for the actual shape. If we have a look at the old maps we got with NOEMA, you can see in the different channels, you see here the cavity on the north, the cavity on the south, and in the central channels, you see the equatorial structure. In fact, thanks to this constant velocity gradient, when you do position velocity diagram along the symmetry axis of the object, what you get is not only the position velocity diagram, but you also get the structure of the nebula. because you can directly translate the Doppler velocity you see into position along the line of sight. I'll come to that later. And as I said, this velocity gradient translates into a kinetic age of 1200 years for this object. So what is new? The new thing is that we have revisited the object with the new instrumentation. This new iron interferometer NOEMA is not only that consists in more antennas. The other big advantage from the previous observation is that you have more bandwidth, and then by observing in 2 settings, we have been able to sample to map 32 gigahertz in these 2 settings. And these within this 32 gigahertz, we have been able to put 3 different isotopic substitution of CO, 13CO, C18O, and C17O. One line of at least one line of these species, which are tracers, typical tracers of shocks, but also of PDRs. Sorry, this is a mistake here, PDR regions. And in addition, several lines of species like sulfur monoxide and sulfur dioxide, which are tracer of the dense gas, but also of shocks in dense gas. Okay. This is a summary of what we are getting from the new observations. If you have a look at any line in the survey, they will come in one of these 3 flavors. I mean, the CO isotopes, in fact, are the only ones that show you the typical velocity position diagram we already knew from CO and 13CO. So it's only C18O and C17O, the other 2 that show this velocity position diagram. If we have a look at the dense shock tracers like SO and SO2, the only thing that we see is the equatorial structure, but now we see a torus and a compact component right in the center. And if you have a look, for example, at HCO plus or HCN or HNC, then you see the equatorial structure again, the 2 polar tips, and something that I'll discuss later right at this position. And as I said, any line should come in one of these 3 flavors. One thing we have done with this data set is that because we have this constant velocity gradient, we can use the velocity we observe to derive the position along the line of sight. And if you do that, you only need to take a distance. And by using this transformation, you can play with different angles, inclination angles, and you can even fit the inclination angle because you really want to have an output that preserves the cylindrical symmetry. If you do that, we derive an angle of 40 degrees for the source over here. And then once you realize the source is also very cylindrical symmetric, then you can average along the symmetry axis, and you can also average data between the north and south lobe because they really look the same. And then after doing that, you get something that I will call the 3D reconstruction of the structure of the nebula. But note that this is direct reconstruction from the brightness temperature. So this is not brightness temperature. This is not density in CO. This is not excitation temperature. This is the real 3D reconstruction of the brightness of 13CO. If you do that with C17O and C18O, you realize that both species show the same structure. They occupy the same space, so there is no fractionation effects, no special photodissociation in any of the 2 species. And because of that, we can use the line ratio we already derived from single disk observations to derive the isotopic abundance, isotopic ratio between 17O and 18O. And we found a value of 1.6. This value corresponds, according to standard models, to an initial mass of 1.7 solar masses. The problem is that these standard models for stellar evolution predicts that a 1.67 solar masses at the end of the AGB, and this is beyond the end of the AGB, must be carbon rich. But this guy is all rich. We are suggesting that maybe the sudden event that resulted in the ejection of these 0.9 solar masses in a very brief event what produced was a prematurely end of the AGB evolution, and that's the explanation why this object, it didn't have the time to turn into sea ridge as it was bound to be. Now let's have a look at the SO lines. The SO molecule has a more tight energy levels in the spectrum, and thanks to that, we have up to 6 lines covered in our observations. We have detected 4 of them, and we have obtained upper limits for
2 minutes.
for the other 2. And since we have several lines, we can do one thing is that combine this transition in what is called the rotational diagram formalisms, including the upper limits in a Markov chain Monte Carlo, and derive true excitation temperatures for the structure of this central equatorial component. You see we are deriving temperatures from 10 to 50 Kelvin, and true particle densities for this species in this central equatorial component. As you see, there is a central component and then this kind of torus with this funny shape. We can compare that with 13CO, and we see that this torus, it's outside the bright region emitting in CO, but is coincident with the OH masers, and in fact is just inside a torus we have also detected in the continuum that is represented by this brown circles here. We also are detecting the continuum, the central component. Putting all together, we think that this this structure seen in SO is due to shocks in the equatorial direction that are enhancing the local abundance of this particular species in this equatorial place structure. And to finalize the talk, let me talk about a little bit about HCO+. The surprise with this molecule, as well as for HCN and others, is that when you have a look at the stream velocities, you detect not only the tips, the 2 tips of the nebula located over here, but you also detect in molecules the knots that are emitting in optical lines due to shocks. And in fact, if you examine the intensities, the contrast between the CO and these other species is between this tip and this knot is between 5 or 15. So either CO is depressed in this knot, or the abundance of these 2 species is enhanced in this knot. Probably what is happening is both. And if you compare the velocity at that position, you see some kind of horizontal structure, which is very similar to what is observed, for example, in vibrational excited molecular hydrogen. And in fact, is compatible with what you see in the optical forbidden lines, except that in this case, the dispersion of the velocity is larger. We believe that this emission in this knot is due to this kind of PVR environment, because the shocks in those places are able to ionize the material. And just let me finish the presentation with a summary of what we have found in the target. Thank you.
Thank you very much, Javier. Well, so this confirms the thing I was saying before. This is a super object to do detailed modeling. So any questions from the audience?
I have a question.
Yes.
No, go ahead.
Hi, a very nice talk, and I've been fascinated by this object for quite a long time. And my interest is that, this is a PPN. What do you think it's going to look like when it eventually turns into a PN? Because I have to say that amongst the thousands of these things I've been looking at, there's nothing really quite like this in terms of what a PN looks like.
Okay, let's have a look at where the mass is located right now. The mass is located in such a structure. I mean, this is not density. Remember, this is a direct reconstruction from 13CO. If I have 2 different transitions of the same species, I will do the same game. I play with SO and I will derive. But this is more or less the structure of the thing. You leave this thing to span self-similar, and then you turn on photodissociation of molecules from the from the UV, from the interstellar UV, and also from the central source when it becomes hot enough, and then you will have the answer. And well, probably you need to put some, I mean, the fast wind from the central source when it becomes hot, and that will be the answer. I mean, this will be the starting point for modeling.
Yeah, that's where the mass is, and the mass is going to get affected by what happens to the central engine when it heats up, turns on, starts ionizing the surrounding material.
So most of the material is located here. So what is going to be left is what is left after the photo destruction and photo ionization of this material. You probably get a very, I mean, ultimately, I guess you will probably get a ring nebula, because the densest part of in this guy is located at the equator.
Okay, and just following that, what kind of time scale are we talking about to go from what we see now in terms of the mass distribution and molecular material to what you're going to see in ionized gas N years from now?
Probably talking about another 1,000 years or so is when
very quick.
The central,
Yeah. Okay. Thank you. That's what I thought.
And then the shape of the nebula will be exactly the same as twice bigger.
Okay. All right. Thank you.
Okay. We have a question by Vincent. Go ahead, please.
Hi. Thank you very much. It's just absolutely fascinating stuff. I have a question about those tips. I mean, in numerical simulations, one is always worried that you very frequently see those tips appearing, but one is always worried that this might be due to spurious effects at the symmetry axis. That's a real worry with the modeling. Could you remind me, please, in your reconstruction, what the velocity is at those tips, because I didn't quite pick that up.
This tip over here and this.
Yeah, that's correct. Yeah, that's what I mean.
If you do that projection, that will be 70 kilometers per second.
70, only 70 kilometers a second.
Only 70.
You said at the disk, the wind was more like 700 or something, if I remember correctly.
There is a very tenuous wind, very weak, with a velocity of 700, rising right from the central source. Okay.
Cool. Thank you very much.
So, and you can even see that the tips are detached, but you also see in the optical image some protruding thing over here.
Mm-hmm. Okay. Cool. Thank you.
I have a question from Noam.
Yes, Javier, very impressive. This object, yes, it follows us. My expectation from theory that this event, as you said, happened in a short time. So any binary interaction will have some asymmetry with respect to axis symmetry along the line, because the interaction starts at one point. Now, this looks very symmetric, but in your velocity plot, it seems that the red shift and the blue shift parts are not identical. Am I right seeing that?
Yeah, but the problem with this velocity plots, and that's something that goes into the 3D reconstruction, but after making it symmetric, it disappears, that you are also playing, you may have problem with the opacity. I mean, you have self-absorption at some point. So this thing you see, I mean, you probably are talking about this being
but this is moved away from us and it's stronger.
Yeah. Well, I should agree that it's not perfectly symmetric. It's very symmetric. It's one of the most symmetric sources I ever studied, but have a look at the continuum. There are features that deviate from symmetry. This is a line, and you see these blobs, this and this blob are real, and this torus is not symmetric either. I mean, this part of the torus is missing, and this is not well aligned with the axis. So it's very symmetric, but it's not perfectly symmetric. And also the blobs you see in emission lines are not exactly the same on the north and the south. But yeah.
So I think it is very important to look for these non-axis symmetric features, which can also support the short time interaction. And Carmen was very, I think, did a good thing by comparing to young stellar object. That some young stellar object, we some similar jet, like Vandra has worked on that, and I did, and comparing young stellar object to planetary nebulae, not only LBV and massive stars. So these features are very important. It will be good, you know, to devote some, discussion to these non-axis symmetrical features.
To the deviation from the axis symmetry.
Yes,
that's something that can be even evaluated, numerically. No, yeah, that's a good point. I have a look at it.
This is my wish list.
Okay,
to look
that's your wish list.
I put it in several previous APN meetings. Look,
well, maybe in 11 months you get something for a birthday person.
Thank you.
So there are a couple of questions on Slack from Reed. Reed, do you want to make the question yourself, or do you want me to do it? If you want to speak, just go ahead.
Do you hear me?
Yes, you can hear.
Yeah, you detected HCN and HNC, and I was wondering whether the velocity structure and the extent of both molecules are the same, or did you see a difference?
No, they're roughly the same, except that both HNC and CN are weaker, and then I can guess that the structure is more or less the same, but the noise is it's at the limit. But I will say that the well-detected regions, that is the central part, this is pretty much the same, and there are hints of emission in HNC and CN, both in these regions too. The problem with the CN, of course, is the hyperfine splitting, and then the velocity structure gets all mixed, but they are roughly the same, yes.
So they also appear in the knots?
Yeah, they are appearing at the knots, at the tips, and at the equator.
Okay, thank you.
Okay, I've been told by Martina that we can keep discussing as long as we want. So there's another comment on Slack by Miguel, Santander-García. Miguel, do you want to make your comment?
Well, it's just a comment that if in the case that M192 is actually undergoing common envelope ejection, then what we are seeing there, these 0.9 solar masses, would account for roughly for the whole AGB envelope of a star with initial mass 1.7 solar masses, as Javier said. So just to highlight this.
Yes, I wrote in this Slack, in a simple evolution, yes, but what if the companion was, say, 0.3, 0.4, I don't know, 0.5, ejected all the envelope, but then it reached the core, was tidally destroyed, and formed a new envelope. So the post-AGB we see now is part of the mass of the companion, which is not there anymore. I don't know if this is a scenario, but this is a possibility.
If you have such a thing, then the argument of using maybe the oxygen isotopes to weight a star is not applicable anymore either. So you end the game. I mean, if the abundances are not the standard ones, then.
Say it again. So is it possible?
No, what I mean is, if you have a mass transfer, then the other point will be that to derive the initial mass of the star, we use the oxygen ratio, and then this may not be right if there is a significant mass transfer between the two.
No, but it happened after the ejection. Most of what you see in the nebula is the original envelope.
Okay,
but now
then,
the post-AGB might contain some of the mass of the companion, or all of it. I don't know. I didn't work out the scenario. Okay. But we should keep in mind that in many cases, common envelope evolution ends with the destruction of the companion, or the merger of the companion with the core.
Yeah, so it will be a mix. Then if it's a mix, then maybe the oxygen ratio is not telling you that.
But Miguel, it's a good point, yes. Another one to this interesting, yeah.
All right. Thank you very much for the questions and the answers. And we are going to take a short break now of 10 minutes. So I guess we can, we'll meet here again at what? At 11:05? Yeah, 11:05. So see you in a bit.